Recorded is rolling. It's Thursday, August 18th. This was my original plan for day. We're going to get through all of this right here. And then dimensional analysis is a really handy tool that I'm going to take some time on. So I'm going to postpone that to tomorrow. It's going to be our plan. All right, then you guys remember that. Oh, here it is. Okay. Last couple days, we've been looking at trigonometry, and I'm planning to you guys to finish. Get your guys' page out here. To do all five of these lab triangles. I did two of those with you guys, and then on the other side is just the pure math side to pick any five of those. And I've done three of those with you guys. So we should have a few minutes at the end of class today, and then I can walk around and help you guys out. Any questions you had, maybe possibly how to use a protractor. I still have some questions about that, or how to do some of the calculations. And then a lot of you guys have already turned this in, but if you haven't turned it in yet, then turn that in to that break tray right there tomorrow, Friday. If you finished it already, then feel free to turn that in early. Okay. All right. Some other announcements going on. All right, so a few days from now, Monday is going to be a weird day. There's like some new test or something going on. So the way the schedule is going to work is you guys are going to be in your first period for 2.5, 3 hours. Then we're going to skip second and third altogether. So I won't see you guys at all on Monday. And then you guys are going to pick up on that fourth period. That's where it's going. And then the week after that, right before school starts, 8:33 in the morning, there's going to be a rocket launch. It's going to be a rocket to the moon. Which I don't see very often. No, it's unmanned. It's just a bunch of robots, but it's pretty cool. It's going all the way to the moon. So there you go. Right. Yeah, let's get going. Scientific method. Cover that. So modern science really only goes back to a few hundred years ago. Like one of the first scientific experiments that was ever done goes back to 1589. You guys know Leaning Tower of Pisa over in Italy? So a guy named Galileo went to the top of Leaning Tower, dropped different masses from the top. Here's our lab masses, heavy stuff, light stuff, and what do you think? What do you think the common thought was at the time? Say if you go back a few hundred years ago, what should hit the ground first, the heavy thing or the light thing? Okay, so everybody was thinking the heavy thing, but what do you think the actual result of that experiment was? Same time, everything did hit the ground at the same time. Freaked everybody out. That was one of the first examples where of this right here, the scientific thinking. So what is this scientific method? Scientific method. Okay. Let's go over the maybe like a pretty standard textbook process list of steps. Okay. Now, different textbooks you open might have this worded a little bit differently, and even different questions that you're trying to answer might involve a little bit different process, but it's a pretty standard like bread and butter go-to. What's a good starting point for scientific method? Hypothesis. Even before that, yeah, question. Some textbooks say problem, question, a problem, observation. Yeah, yeah. Okay. I'll say question, observation, problem. Usually second is listed as background research. See what's already out there. Maybe your question has been asked before and there's been some kind of approach to try to answer it already. Maybe you can get some insight. I hear a lot of you guys saying hypothesis. So here we go. Here's hypothesis. Yeah, that's right here. What is a hypothesis?
Educated guess.
Educated guess. So yeah, I think this is how this phenomenon works, or maybe this is how these variables might be linked together. A lot of times it's written as an if-then statement, like if you change this variable, then this other variable will change like this. For example, going back to just last week, you guys remember we were measuring lots of properties of circles? If you double the radius of a circle, what happens to its circumference? Should the circumference also double? Yes, it will. Okay. If you double the radius of a circle, what happens to the area? Maybe you say, I think if I double the radius of a circle, that the area would quadruple. And that's what you guys found last week, right? Something like that. Some version of that. Now, if you have a true, correct scientific hypothesis, should your hypothesis, it's going to be an either or, it's one of these, right? Should it be only verifiable, or should it only be falsifiable? Okay, one of those is correct, and one of those is not correct. Let me see a show of hands. What are you guys thinking? If you have a true, correct scientific hypothesis, how many guys think it should only be verifiable? How many guys think it should be only falsifiable? Yeah, you guys are on. You guys got that. Yeah, you guys are right. Okay. Now, why is that? Because if you have some question about how some phenomenon in the world works, and you design a hypothesis in such a way that you could only ever prove yourself correct, then at the end of the experiment, well, big surprise, you're only ever going to prove yourself if you ever set yourself up to only ever be correct. So you haven't really learned anything, right? You haven't really made any knowledge gains in the world, right? Now, why would you want a hypothesis to be falsifiable? Oh yeah, what do you think?
So you can see what's wrong with it.
Right, yeah, it's something that actually could even possibly fail, right? Can you poke holes in some idea, right? So suppose you thought, well, if I double the radius of a circle, maybe the area should go up, maybe it should also double. Well, that would be something that could be falsified, right? Even the correct answer, if you double the radius of a circle, that the area actually quadruples, which is what it does, right? That is something that you could test, right? Could possibly be false until you get the numbers and say, oh, actually, that is true, right? If you look at all the science experiments, the millions of science experiments that have ever been done, right, they've slowly narrowed humanity's knowledge of the universe towards like some like outcome of truth. But really, all that's ever been done is just to eliminate all the wrong possibilities about how things work, and then whatever's left as is probably what's correct. Unless there's maybe some other possibility about how something works that nobody's thought about yet. Maybe you guys one day, scientists come up with new ideas like, hey, nobody's tested this yet. Okay, yeah, so falsifiable hypothesis. Okay. This I should say too is opposite of how our brains are wired to think. Like coming into the world, our brains are naturally wired to think more like lawyers than like scientists. Lawyers, you have some idea about how something works and then you make a case for it. So what your brain naturally wants to do is to seek out information that, and this is everybody's brain, this is just part of having a human brain, right? Is to seek out information that already aligns with how you think things work, and to notice that, take note of that information, and to actively ignore or dismiss or put away information that would contradict the way you think things work. Okay, that's some fluke, that doesn't really count, right, to dismiss it. Okay, it takes like training, like going through like science classes, learning science to learn this type of thinking. Falsifiable hypothesis, which is part of the scientific method. Okay, so now we've got hypothesis. Now what? Yeah, experiment, the heart of the scientific method, experiment. Okay, so use last week's activity as an example, right? Change the radius of a circle, you have different radii circles, and then you can measure, okay, what are the different circumferences, what are different areas of each circle. Okay. Then I'm gonna go data analysis. Okay, so you put all those values in a table, different radius, different circumference, different area. I would give you guys another column to do radius squared so that you can make graphs. Ooh, graphs. You guys think graphs are part of data analysis? Okay, this variable relates to this variable. This looks like a parabolic relationship. This looks like a linear relationship. Okay, and finally, you can come up with a conclusion. Okay, so there you go. There's a pretty standard textbook model of a scientific method. Yeah, no, depending on the problem you're working with, may not fit into that exactly, but the pretty good go-to method right there. Okay. All right. Ooh, let's talk about measuring systems. Right. So actually, just for comparison, I want to talk a little bit about counting systems. Right. So all the math you've ever done, you guys have used a base what system? Base 10. Right. So we have individual characters 0 through 9, and then it just rolls over. We use the place value system. Okay. Now, if you go way back in ancient history, I bet you guys are familiar with Roman numerals, right? Like if I say IX, what is that? That'd be 9, right? But that is not a place value system. That's just, it's good for counting, but not even that high, right? You guys ever seen like the credits of a movie? It says like MC, and it just has like whole string of letters, like, what is that, right? So you can kind of count with it, but that's about it. If you want to do any higher level math, you kind of have to use a place value system. Now, is there anything special in the universe about base 10 specifically? Not really. In the past, different societies in the world have used like base 5, base 8, base 10, base 12, base 16, base 20, base 60. In fact, base 60 that the Babylonians used, like modern day Iraq, is why we still to this day have 60 seconds a minute, 60 minutes in an hour. Different. Ancient Chinese even use base 16. Even the abacus today can handle base 16 because of that. So the world's kind of settled on base 10 though. I don't know, maybe someday we'll get a visit from the aliens like, oh, the rest of the universe is on base 12. Oh, look at you losers on base 10. But that's what we got, and that's fine. It works. Okay? But then what about actually measuring quantities, right? Like if I want to know what is the mass of this lab weight? Well, there have been kind of two standards that have stuck around. Right, we get US customary units that come from England. We can measure in pounds. So you say, oh, this would be like 2.2 pounds. Okay? And then there's the metric system that we're going to use like 99% of the time in this class, right? System International, the International System of Units, metric system. Who can tell me what country does the metric system come from?
France.
France. And what time period?
1700s.
1700s. Yeah. How about 1789, 1790s? You guys know about the French Revolution, right? So there was the American Revolution, 1776 to 1780s, and then the French people were inspired by our revolution. They said, let's have our own revolution. They got very choppy, and they not only wanted to have a political revolution, but also reform a bunch of other things at the same time, including scientific units of measurement. So let's look at some systems of measurement they came up with. I'm going to start with how about distance or length? How are we going to measure distance or length in this class? Are you guys thinking meters? Yeah, centimeters is fine too. Centimeters, meters. So those are both metric units, right? Now the base unit is meter. Here's a meter stick. Okay, so flash it here for the camera too. But you guys know 1 meter. It's 3 point something feet. A little bit more than 3 quartiles. Right? Where does that length cover? What's special about this exact length? Like at some point in history, probably 1790s-ish, somebody said, we're going to use that length right there as the standard unit of length. And where does that come from? Oh, it comes from here. Here's the Earth. A lot of the properties of metric system, by the way, are tied somehow to properties of Earth or water. I mean, this is the original definition of a meter. If you go from the North Pole to the equator, and you divvy that distance into 10 billion parts, guess what you get? 1 meter. Okay. That was the original definition. A lot of units are again, like properties of Earth, properties of water. In the meantime, this project was just finished in the last few years. Scientists have changed every single definition to be based on universal constants. The modern definition of 1 meter is the distance that light travels in a very, very brief amount of time, or time fraction of a second, because the speed of light is a universal constant, right? Through a vacuum. That doesn't change. Right, so there you go. There's meter. Now, if you take 1 meter and split it into 100 parts, so you guys just mentioned centimeters, right? There's 1 centimeter. Suppose I make a cube, a box, 1 centimeter by 1 centimeter by 1 centimeter, little cubic box, and I fill that with water. Right, fill the thing with water. Guess what the mass of that box full of water would be?
1 gram.
1 gram, right? Which is about the mass of a paper clip. Here's your smallest lab weight. This is 10 grams. So this is like 10 of those. How about, what if you have 10 by 10 by 10 of those? So like 10 centimeters. Here, I'll show you guys. 10 centimeters by 10 centimeters by 10 centimeters. Big old box. You fill that with water.
1 liter.
It is 1 liter volume. That's 1 liter volume. And guess how much mass that is?
Kilogram.
1 kilogram. Now that's the original definition of a kilogram. Of course, if you change the temperature of that water, then that goes out the window. So now, and this was the last one to be standardized according to universal constants, just in the last few years, even like after I started teaching. So in your guys' lifetime, the modern definition of the same mass, I mean, it's equivalent amount of mass, right? It is tied to a universal constant called Planck's constant, which is the ratio of energy to frequency of light. Right? So that's a universal constant. Right. Here's probably a good time to switch my screen over, show you guys some other units. Okay, let's see, share screen 2. Okay, we don't care about that slide in particular yet, but this one. Wait, zoom. There we go. All right, SI System International, International System of Units. Okay, so at the top there, oh, kg, that's kilogram, right? Now, you might be thinking to yourself, well, hold on, I just been through chemistry. I know chemistry will deal with the grams a lot. So from now on, you guys are going to know that it's not grams, but kilograms. That is the base unit. Okay? And that becomes important when we start to build composite units. As an example, force. What have we been measuring force in? Like all those hungry monkeys, we're pulling in how many what? Newtons, right? Do you guys see capital N newtons as a unit up here? No, because force is a composite unit. I'll tell you what force is. So 1 Newton is equal to 1 kilogram meter per second squared. So you can see how like kilogram is an ingredient that's like baked into 1 Newton, right? So now you guys know, because 1 gram is just so small. So kilogram is the base unit. It's the only one that has a prefix attached to it, right? Kilo is 1,000, right? So we got that. I also want to contrast this with the US customary units that come from England, because those units, you guys know, have all kind of weird conversions, like 5,280 feet in a mile, and stuff that's not really logical. SI system is all factors of 10, right? So one thing that the metric system does really nice that the US customary units are terrible at is distinguishing between mass and weight, right? So 1 kilogram of mass is about 2.2 pounds of mass, but pounds is also used for force. But those are different concepts, right? Like if you have 1 kilogram of mass floating around in space, is it still 1 kilogram of mass? Yes, it is. The same amount of material, same amount of inertia. You push on it, it accelerates the same. Okay? But what about weight? Weight is a force that pulls straight down. It's a completely different concept. So in the US, if you talk about pounds, you say, well, you're talking about pounds force or pounds mass. It gets really muddy and confusing. But the metric system is really good about saying, no, kilograms measures mass and newtons measures the force. Those are completely different concepts. Okay? Okay, meters. Oh, well, I told you guys about meters. You guys know 1 meter stick. To take about 40 billion of those that wrap all the way around Earth. Okay, there you go. 1 second could measure time, right? 1 second measures time. Now you guys know what 1 second is. Take 1 Earth rotation, divide that into 24 hours, divide that into 60 minutes, divide that into 60 seconds. There you go. Now that's kind of the only one that is related to something that's not like factors of 10. Right? Quick historical side note here. During the French Revolution, there was an attempt to also make time, align time to a base 10 standard. So very briefly, just for a few years in France, they had 10 days in a week, they had 10 hours in a day, 10 minutes in an hour, and 10 seconds in I think I might have it wrong. 100 minutes in an hour, 100 seconds in a minute. And when you run all the calculations, it turned out that one of these metric seconds that has since left, we don't use that anymore, right? It actually is pretty close to what 1 second is that we do still use today. So what you think of on the clock is 1 second, yeah, that is 1 second. It's the same thing, right? Now the modern definition of 1 second is not tied to Earth's rotation anymore. Now the modern definition of 1 second is it has to do with like the vibration of a cesium atom, which is really constant. And even Earth's rotation changes a little bit as time goes on. Okay? Like as the moon is tugging on it. Now those 3 right there, kilograms, meters, and seconds, that's going to carry us throughout this entire semester. So fall semester, that's the only 3 base units that we're going to use. And we're going to mix and match those all different ways to create all kinds of composite units. I gave you guys an example 1 already. Kilogram meter per second squared is a unit of force. That's a Newton. That'll make sense a few weeks from now. How about this? Area. Could that be like square meters or square centimeters? Or so that's just meters. Volume, cubic meters, right? How about speed? Meters per second. Velocity, meters per second. How about energy? Kilogram meter squared per second squared. Right? So these 3 guys right here are going to carry us all the way through to the break. Then what about these 4 guys over here? That's more like a spring semester. We'll touch on these, but let's talk about them right now. What do you guys think that capital A stands for as a unit? Good guess. Pressure is actually Newton per square meter, which just goes back to these 3 guys again. Right. How about, are you guys thinking electric current is measured in amps? There you go, amps. Yeah, which is short for amperes. Right, got it. Right. So that'll be next semester thing. What do you guys think the unit capital K stands for?
Kelvin.
Kelvin, good call, which measures temperature, right? And you might think Fahrenheit or Celsius, those are okay, but those are just relative scales. But if you ever plug a temperature directly into an equation, you have to use Kelvin because what's special about Kelvin?
0 is an absolute zero.
Zero is absolute zero, right? So Kelvin doesn't go negative, right? Because, right, there's no such things like negative temperatures if you're using equations, right? Right. And then, how about, oh, moles? You guys know that from chemistry, right? What is 1 mole?
0.68 times 10 to the 28.
Yes, something like that, right? It's like
How many atoms?
6 times 10 to the 22, something like that. It's just a crazy, crazy big number, yet used for counting atoms because atoms are so crazy small. I guess the big scheme of things is just a really big number, right? But it's used to like count like atoms in chemistry. Okay. And the last one on here, what do you guys think that CED stands for?
Just putting that cadmium earlier, that's what mine.
Ooh, good guess. Think something different. How about this? Let's say you're looking at the sky at night, you're seeing all the stars, you know, twinkle, twinkle, right? And then you look at one, you're like, whoa, that is a really bright star. I am pretty sure that star was not that bright last week. I wonder if it's blowing up or something. Hey, how could I quantify how bright the star is? Maybe some number of candelas to measure luminous intensity. And there you go. There's all 7 base SI units. Any questions on any of those? There. All right. Next thing. Let me switch the screen back. You know what I'm going to do is pass around this 1 kilogram mass so you guys can actually feel this and get your hands on this. So pass this guy around. So there's 1 kilogram for conversion. Remember, that's about 2.2 pounds. So have a few of those, maybe a bowling ball. What measuring tools are we going to use? Let me see if I got the. Here we go. Let's do it this way. Just have flashes at you guys. Okay. So variable unit tool. Displacement, we're gonna measure in meters, maybe using either a ruler or a meter stick. That makes sense. Okay. How about angle? You guys think we're gonna use this guy here, a protractor? Okay, and we're gonna be using degrees. Now you could also measure angle in radians, which mathematically is better for a number of reasons. You can plug it directly into formulas, but save that idea for later. We're going to mostly use degrees. Okay, degrees you can use as long as you're using like sine and cosine, and your calculator can program that. Time, you guys going to measure in seconds with a stopwatch. I'm going to have you guys use your cell phones for stopwatches. Okay, so that's going to be your time tool stopwatch. Okay. V, velocity or speed. Right. So speed is the scalar, velocity is the vector if you have direction implied or specified. Okay. Here is a new tool, this motion detector, the speed sensor. We just got these brand new a few weeks ago. So none of my students in the past have ever used these before. I will demo this for you guys real fast. I'm really excited about these. You guys get to get your hands on these and measure speed directly. Okay. Now speed, do you think if you had 2 points and a time between those 2 points, you do distance over time, get the speed? Right, and that's what's going on inside this thing, okay? Because it has 2 sensors right here. It's not showing up well on projection, but maybe on the camera. I don't know. There's like 2 sensors. So let me turn this thing on. The unit is blinking meters per second. You can like swap out the unit, but let's go meters per second. Okay, let's try this out. 1.27. 1.27 meters per second. Okay, let me try again. Let me clear that up. Take 2. 2.54. Ooh, even faster. All right, so that will be a speed sensor. You can directly measure speed. So that'll be exciting times. Got some new labs we can do now. Mass. So the base unit for mass is kilogram, although see your lab weights, the biggest one is 1 kilogram. So I mean, anything smaller like this is 200 grams. A lot of the lab pages might just go to grams just because that's the magnitude of your lab weights. Okay. So what can you use for that? Here is a digital scale. Now this digital scale, say I put 200 grams right here. Take a number, it's gonna pop up on the screen that says 200 grams. Yeah, right. Now, if you pause for a moment and think, oh, hang on a minute. How is it knowing that? Do you think actually that this mass at the surface of Earth has a particular weight that's pushing down on this plate? that is registering like some force? And do you think that scale is translating and saying, well, as long as you had been at the surface of Earth, then this mass would have produced a weight that would, so it had to have been 200 grams, right? Right. This is technically reading a force and it's translating it back to the mass that would have created that force. Right? Here's what I'm trying to get at. If you take this to the moon, is this still going to read 200 grams?
Probably not.
You're right, it would not anymore. It would read 1/6 of that, whatever 200 divided by 6 is. Okay. But let me switch my screen back over. Let's see, present screen 2. Actually, I want to do this one right here. You guys see that triple beam balance? That lab closet right there has one of those. Somebody's borrowing it right now. So the best I got for you guys right now is this picture. Now this works on a different principle. What if I put that 200 gram lab mass right here? You guys ever been on a seesaw, like as a kid, teeter totter, like a seesaw? Right? Suppose you have a friend that's a different weight than you can slide them around and like balance that thing. Right? This works on that principle. You guys see these sliders? Right? Let's see, show of hands. How many guys have ever used this tool, triple beam balance? Most of you guys. Awesome. Some point in class this year, I want you guys to be able to get your hands on this. You got 100 gram slider, and the far back is 10 grams at a time, and the one's closest to us is 1 gram at a time. Right? You slide it until it balances. Right? Now, this works on a different principle than the digital scale works. This works on a principle of torque, like the seesaw, right? Like force times lever arm. Right? So, if you took this tool to the moon and you put 200 grams on it, is this still going to tell you 200 grams?
Yeah.
Yes, it will. Yeah, this will work perfectly fine on the moon. Right? We're just that digital scale operates on a different principle. Okay, so switch back over here. Okay, figure this stuff out. What's next on our list? Oh, force. Right, force measured in newtons. Which, think about it, really probably how that digital scale was kind of working, right? What are you going to use to measure force? I wrote force probe here. That's more of an AP thing. That's a term they use in their rubrics. But we're going to have the spring scale. You guys see a spring scale? Right? Well, look at this. It says N, capital N. What does that N stand for? Newtons. So if I hang this this lab weight right here, think it's going to pull to the number of newtons? Let's see what this says. No, it only works vertically, but I'm going to stop it right here. Right, let's take a look at this. It's almost exactly 2 newtons. It's like a tiny bit short of 2 newtons. Okay. Oh, so what do you think the weight of this lab weight is? You guys think it's almost 2 newtons? It is. It's like 1.9 something. So usually I'll just call it 2 newtons. It's a tiny bit short, shy of that. Okay. Hey, do you guys see the spring right here? See the spring? Do you think the more I pull on the spring, maybe by attaching heavier and heavier weights to it, that spring pulls back with greater force until it reaches equilibrium? Right? Right. In fact, the spring, the force it pulls back with is proportional, directly proportional, like linear relationship with how far you pull it. That's called Hooke's law, and that's why this works. That's why the scale is scaled linearly, like 2 newtons, 4 newtons, 6 newtons, 8 newtons, 10 newtons. But now this Brown scale goes up to 10 newtons. There are other spring scales in the lab closet that have stiffer or less stiff springs that are good for different time zones, right? Now, if you rotate the spring scale, on the other side, it says it's grams. Ooh. And then hang this again, stop it, rotate it, 200 grams. Guess well, it was at 200 grams. Okay. Now, if you took this to the moon, would it still read 200 grams? It would not read 200 grams because it works through a principle of force, right? So remember, this is actually reading newtons. That's what technically reading is newtons. The grams is just what mass would have provided that force had you been at the surface of Earth. Okay. So spring scale for newtons. I'll give you guys a lab here in a few weeks that just involves like using this like 10 different ways. You can see lots of different things you can do with that. Next one on this list. Oh, I got it right here. Current measured in amps or voltage or potential difference measured in volts. You can use a ammeter or a voltmeter. Now those are different tools, but I have this orange digital multimeter that can handle both of those processes. Okay. This is an electricity concept, right? So if I turn this toggle, I can turn it to volts to measure like voltage or potential difference. Or I could turn this toggle over to amps or milliamps to measure the current. And that rounds out the list. those are, I'm pretty sure all the measuring tools you're ever going to need or get your hands on in this class. All right, guys, good with this? Okay. Yeah, go ahead. Computer, check out right there. Okay. Okay, next thing, scientific notation. So in this class, do you think at some point you're going to calculate orbital speed for, say, a satellite going around the Earth?
Sure.
Do you think you'll have to know the mass of the Earth to calculate that orbital speed?
Probably not.
Do you think the orbital speed is different on different planets?
Yeah.
Yeah, right. So here's the mass of Earth. Kilograms. So there's that 1 kilogram mass being passed around. If you have that many of those, that would be the entire planet Earth. Now, do you want to sit here punching that number in your calculator screen to calculate orbital speeds? That'd be kind of cumbersome, right? What if I missed that zero? Or how about this though? Are these zeros even significant, or are they just placeholders? They're just placeholders, right? I don't really know that that zero is a zero. It might be a 3. I don't know. Right? Hey, do you think there's a much more efficient way to write this number?
Yeah.
And what is that way?
597 times 10 to the.
Yeah, 5.97 times 10 to the something, right? How about this? To go take this decimal from here all the way back to this units place, that's 24 places. So if you started with 5.97, to restore the number, you'd have to move the decimal back 24 places. 10 to the 24, that's still kilograms. Look at that. Okay. So the rule for scientific notation, the standard version of it, is that you always move the decimal to the units place. There might be a couple of exceptions to that, but that's usually what you do. So 5.97, and then you restore the decimal 10 to the power of something. So like 24 places. Right? Notice it's not times 24, it's times 10 to the 24. What about this? One of the numbers we're going to be working with is called the universal gravity constant, which is this number right here. This is related to actually it's directly proportional to the gravitational force between two objects, between you and the Earth, the moon and the Earth and the sun. Okay. Nobody knows why this number is what it is, but it's been measured to be this. Right? This is a universal constant. Right? How about kind of same scenario as before, right? These zeros are just placeholders. Okay. What's the scientific notation way to write that number? 6.67 times 10 to the, let's see, from here to here is 11 places. So what goes in that power? Negative 11. Exactly. 8 meters squared per kilogram squared. Okay. So guys, negative powers, does that make the number negative? No, that just means it's really small. So you move the decimal to the left 11 places. Okay, guys get that? Now, both of these examples have actually how many significant figures? 3 each. 3 there, 3 there. Right? There's something I forgot to mention about the mass of the Earth. Let's go back to that just for an example here. What if, just suppose, this 0 here actually was significant? Right? In the expanded form, it's ambiguous as to whether it's significant or not. Like, what if you actually know this is truly a 0 and not anything else? Okay? But in scientific notation, if I put a 0 right here, would that 0 now be significant? Yes, because you're taking an effort to actually write it there where you didn't necessarily have to. If I put a 0 right here, now this number has 4 significant figures. And I can say, like, I know to that level of precision that there actually is a 0 right there. Okay. All right, you guys got that? Let's do prefixes, SI prefixes. So, okay. All right, so these won't be all the prefixes that we're working with, but I'll list some of them. Right, let's go base. Let's go factor of 1,000, which is kilo. Here, let's do this way: mega, giga, and then the other way: milli, micro, nano. Right. Obviously, there's a lot more prefixes, but That's kind of the order of magnitude that we're looking at here. Okay? So a base might be just like meters, seconds, that sort of thing. Okay. K, kilo, is a factor of 1,000, which is 10 to the power of 3. For example, kilometer or kilograms, right? Kilo is 1,000 something, right? Capital M, what do you guys think capital M stands for? Mega. And mega is a factor of a what? Million, which is like 10 to the 6. All right. What about, so suppose you have a computer file and it's 1,000 megabytes. What's that called? Gigabyte. I should say too, I bet some of you guys know, computer files are technically a factor of 1,024, but pretty close to those things. So yeah, that's times a billion, which is 10 to the 9. Okay. Oh, what if you go the other way? M, we've been using M all over the place. In algebra, it's slope. As a variable, it's mass. As a unit, it's meter. And as a prefix now, prefix, it means what? Milli, which is 1 over 1,000, which is 10 to the negative 3. For example, millimeter, right? 1,000th of a meter, okay, which I have right here. There's 1 millimeter. Drink. Oh, tiny. Right? If you get 1,000th of that, ooh, you guys see this Greek letter mu? It looks like a U with a tail on it. Mu. What do you guys think that stands for? Micro. Oh yeah, micro, which is 1 over a million, or 10 to the negative 6. For example, microgram. Okay? Taking a medication, it says take 300 micrograms. Right? Oh, and if you have 1,000th of that, what do you guys think that N stands for? Nano. Good call. You guys ever heard nanometer, nanobot, nanotechnology? That's 1 over a billion, which is 10 to the negative 9. For example, nanometer. Okay. So some good prefixes to know. It's not all of them. You could say, oh, what about centi? Centi is 1/100th, right? 100 centimeters in a meter, 100 cents in a dollar. Right. Let's do one more concept today, which is precision versus accuracy. Flip the screen over, and then we'll have a few minutes. I can answer questions that you guys have about that trig page if you have any questions. So precision and accuracy. Right, so I really like this dartboard analogy. Suppose you build a robot, a dart throwing robot, throwing all these darts. What if you are aiming for the target and you're hitting the target every single time? Okay, well, that's both precise and accurate. Okay, so that's all fine and good. Right, now let's go to the top right quadrant. What if you're hitting the same spot over and over and over, but it's not your target? Okay, it'd be very precise, but not very accurate. So you have to go calibrate your machine, right? Right. Now in the bottom left quadrant, suppose that on average your darts are hitting the center, like but they're kind of all over the place. Okay, so you could call that accurate. On average, it's accurate, but it's not very precise. Okay. And then the bottom right quadrant is neither precise nor accurate. Basically. All right, let me switch my screen back over. You know what? I'm just going to throw up some notes from last class for this one, because how does precision and accuracy translate to like measurements in this class? Because okay, well, I got these tools, I got these quantities I'm measuring. Okay, so suppose there were 6 different scales, like these digital scales right here, from 2 different manufacturers. Okay. So here's one manufacturer, the measurer, and the other manufacturer, the knower. I've got 3 scales from this guy and 3 scales from this guy. You guys get that? And I'm going to take this here lab weight, or no, not that one. Let's say this one. This is 500 grams. And I'm going to put it on every single one of these scales, and I'm going to get a reading. Okay? And let's say I get readings like this. First scale says 499 grams. The second one says, no, it's actually 502 grams. The third scale says, you guys are both wrong. It's actually 504 grams. Okay? Okay, and then I switch over to the other manufacturer with these other 3 scales. And I'm getting numbers like this. 501.917 grams. 501.913 grams. 501.920 grams. Right. Now, which of these, or how about this? This bottom scale would be more what? More accurate or more precise? more precise. When you have more digits, that means you have more digits of precision. Okay, so like 3 more digits of precision. Okay, down like 100, yeah, got what, tens, hundreds, thousands placed. Okay. Now, which of these 6 scales is the most accurate scale? As to say, which one is most correct? Well, that might be an interesting philosophical question, because how could you ever really know? Yeah, there's no real answer to that question as to which one's actually the most accurate. Okay? Maybe you could do like a million scales and take an average and something like that. But in science, all we have to measure with is whatever equipment we have, and there's always going to be some built-in error in the equipment, and like maybe your eyes reading the equipment, something like that. So I can't really say which one's most accurate, but I can say that these 3 scales, these D, E, and F, are more precise than A, B, and C. Okay, guys, good. All right, so. Dimensional analysis, I'm gonna save for tomorrow. You guys remember this trigonometry page? A lot of you guys have already turned this in. If you haven't yet, then let's do tomorrow. And let's take the last few minutes of class and I will walk around and help you guys out. Any questions you have?